So I'm happy to have Peter McGrath to give colloquial talk here. As many of you know, that Peter joined our department in 2020, and he was a PhD student at Brown University, graduated in 2017, and after this, he was a postdoc at University of Pennsylvania. And Peter received in 2019 George Follier Prize from American Mathematical Association of America for great expository writing in mathematics. And I am looking forward to hear his talk on calculus operations and bending energy of surfaces.
Okay, well, thanks so much, everyone. It's nice to see some folks here and then some more folks on Zoom. So please do ask me questions at any time, especially if you're on Zoom. I will probably not be looking at the list, so please just chime in if you have some questions there. So I want to begin with a little demonstration. So this is a video of an experiment that was first done by Robert Hooke in the late 1600s, and then more thoroughly about 100 years later by Ernst Chladni. So there's a metal plate here, there's sand on it, and then the plate is vibrated using a violin string. And so you see a very curious pattern that the sand on the plate one more time. The sand moves into a very curious pattern. Where the sand moves is where the plate is not vibrating, not moving, at least the first order. Okay, so at the moment, let me just accept this as a curious phenomenon and then actually get to my slides. Okay. So I want to begin with this experiment. This interested a lot of people, and in the early 1800s, Napoleon offered basically a prize for understanding the mathematics behind the shapes of the sand on these plates. The first progress in this direction was by Sophie Germain, who understood basically the partial differential equation, which governs the position of the displacement of the plate. So if U represents the height above the equilibrium of the plate, X, Y are the spatial variables on the plate, and T is time, she derived this somewhat nasty fourth order partial differential equation for U. So I want now to generalize this setting. So here we were just talking about a moving plate that's bending a little bit, oscillating. And I want to generalize to a setting where I'm now considering a surface in R3. So this will be the analogy of my plate. And this will be a closed surface. And I want to think of this surface as bent or being bent. And I want to look at first how much it costs basically locally to bend this surface from being flat. And so a simple sort of calculation shows that infinitesimally the amount of energy density to bend this plate is proportional to the sum of the squares of the principal curvatures. So let me remind ourselves, if I have a surface in R3, the principal curvatures are two numbers which basically tell us how much the surface is bending. So they can be positive or negative, and I have this little diagram here to indicate how this happens. So if I slice the surface in planes, I can choose a one-dimensional direction of planes if I request that the planes contain the normal to the surface. And then in each of these planes, the plane cuts the surface in a curve, and then I can look at the one-dimensional curvature of the curve in that plane, and then I can take the maximum and minimum of these one-dimensional curvatures over all directions, and these two numbers are the principal curvatures. So this is essentially what Germain understood in the case of the plate. And then we can now take a look at this bending energy density and play some tricks. So the first tricks are some algebraic tricks. So instead of writing the sum of the squares, I can look at these two symmetric polynomials, basically these two variables, their sum and then their product. And those two quantities are of interest to geometers because they are the mean curvatures and the Gauss curvatures of the surface. So the mean curvature ascribes some kind of average to the amount of bending. The Gauss curvature is a little bit more mysterious, but it's the product. So if now I'd like to pass from the bending energy density to the total bending energy, I integrate over the whole surface. So I integrate over the whole surface and I get this quantity here. And the latter term, this integral of the Gauss curvature, turns out to be a topological invariance. This is what the Gauss-Bonnet theorem tells you. So for example, if my surface topologically is a sphere, the Gauss-Bonnet theorem says that this latter integral is always a 2 pi, no matter how the surface is curved. Right. Maybe not a question. So what we learned here is that if I actually care about the shape of the surface and how it's bent, I care only about the first term, this integral of the square of the mean curvature. And here in this definition of what I will call the bending energy or the Willmore energy, I put a factor of a quarter out. This is just a normalization to give a nice definition later. Okay, so we want to study now this bending energy, the integral of the mean curvature squared in surfaces. So there's a lot of study going back hundreds of years, as we saw before. So in the 1920s, it was understood that there was a very nice relationship between this quantity and conformal geometry. So it turns out if I have an ambient conformal transformation of R3, if I have a map that preserves all angles of all tangent vectors in R3, and I take surface and then its image under this conformal map, they always have the same bending energy. So this should be a little surprising because you can imagine that there are conformal transformations that at least locally drastically change the shape of my surface, but globally they preserve this integral. So there's a natural question: what are all the conformal transformations of R3? There's this classical theorem of Louisville that says basically they are well understood. They are very well understood. So you have isometries of R3, so rotations, reflections, translations. These clearly don't preserve the geometry of the surface at all. We also have the dilations, they're conformal transformations. And then we have these inversions. So the inversions are the only ones where you can't basically eyeball their conformal transformations. So the inversions send a point here, Q, to infinity. And Louisville's theorem says that any conformal transformation of R3 or Rn for n big, at least 3, is just a composition of these things. So a fairly simple set of conformal transformations. This may sort of jog your memory in a perhaps unpleasant way if you're thinking about the two-dimensional case. So in the two-dimensional case, conformal transformations are much, much richer. So we know by the Riemann mapping theorem that if I have any two proper domains, simply connected domains of the complex plane, there exists a conformal transformation that takes one to the other. So I just want to emphasize that the situation for n, at least 3, is much different. But that's where we'll be looking for the rest of this talk. So we have now something in our toolbox, which is these conformal transformations, which change the shape of our surfaces, but not their bending energy. So there's some games you can play. So here is a torus and 4 different conformal images of it. And using these inversions, which tend to point to infinity, and rescalings, what you can do is you can basically blow out the torus so it becomes more and more sphere-like. So this last picture is something that's very, very nearly a sphere and has just this very, very small handle. And so you can take a sequence or a smooth family of conformal transformations and basically blow out any closed surface, doesn't have to be a torus, such that basically if it has topology, all of its topologies sort of get shrunk sort of to a point, and then the surface looks more and more like a sphere. So this is possible via the inversions. So this idea will come up several times. So what is the problem we're interested in? This is known as the Willmore problem. And we can ask most simply, what closed surfaces minimize the bending energy? So if I want to consider a surface and say, how cheaply can I bend the surface so that it closes up? This is the basic question, or a basic question. And the simplest version of this question has a very simple and satisfying answer. Willmore, in about 60 years ago, proved that you always cost Willmore energy at least 4 pi, and you can only ever achieve 4 pi if you're exactly a round sphere. So that's the story. Fortunately, there is a very simple proof. So I'll give a proof here in just the case where the surface I'm considering actually has genus 0. It's not very difficult to extend this argument to the case where your surface has higher genus. So what do? We want to write down this proof. The first step I have there is just the definition of this Willmore energy. I have the mean curvature squared. And then I play again a little algebraic trick. And then I simply throw away this first term, which is non-negative because it's something squared with positive coefficients. And then the latter term is again this Gauss curvature term, which from what I said before, gives us a topological invariant, 2 pi times the Euler characteristic. And in this case, I'm assuming my surface has genus 0. So the Euler characteristic is giving me 2, and I get 4 pi. So that is the proof in this case. So we can ask more interesting questions. So I can ask the question, suppose now I fix genus. Actually, this is not the question I want to ask next. So I want to go in a slightly different direction. So rather than asking about minimizers, I can ask about critical points. So rather than a surface that has the global minimum, this energy, can I find a surface where locally I have, say, a minimum? So one direction in which you could study this is via what's called the Euler-Lagrange equation. So you can turn this functional and a critical point of this functional basically into an equation. This is a sort of classic calculus of variations approach. Turns out that this equation is very difficult to study. It's not very useful in general. So again, it's a 4th order equation. So here I have a Laplacian. So that's 2 derivatives. And then the h, my mean curvature, already costs 2 derivatives. So this is a 4th order equation. If you really begin to think about this, this is actually even a little bit worse than it might look because this is the Laplace operator on the surface. So that operator is actually a variable in the problem because the surface itself is a variable. So I'm not doing the Laplacian on Rn. So I go in a different direction, slightly more geometric direction. So here's a fact. So if I take stereographic projection and I take R3 to S3 minus a point, it turns out the Willmore energy of my surface turns into the area of the image surface in S3, plus basically the version of the Willmore functional in S3, where here the mean curvature is the mean curvature of the image surface in S3. So what this means is that if I'm searching for critical points of this, I can search for critical points of these 2 things in sum. And it's not very difficult to show that certain surfaces in S3 that have mean curvature exactly 0, these are called minimal surfaces, are critical points for the Willmore functional, or rather their stereographic images are. So if we can understand minimal surfaces in the 3-sphere, they are at least critical points for the Willmore function. And fortunately, there are many examples of these latter objects, minimal surfaces in the sphere. So there are examples of each genus, this is known. And my collaborator and I constructed some other very high genus surfaces, minimal surfaces in the 3-sphere. So I'm about to draw some pictures of these objects. So these are examples of some stereographic projections of some minimal surfaces in the 3-sphere. So these are actually surfaces in R3, critical points for the Willmore functional. And I have genus 2, 3, 4, and 5. So there's a full family of these for general genus. And what happens as you take the genus higher and higher is basically you're beginning to see basically 2 spheres that are connected by a large number of handles there. So So the second types of surfaces, the ones that I actually constructed with my former PhD advisor, look like what I call double spheres. So in this picture, it's a little bit difficult to see. So this is another stereographic projection. It's easy to see sort of an outer sphere. It's a little bit harder to see that inside of this, there's basically another sphere. And then the two spheres are actually connected by lots of little tubes, basically. So this is a single connected surface with high genus. Not actually sure what the genus of this surface is. So these are also critical points for the Willmore functional. So let's, after this diversion, get back to our original question. So I want to consider minimizers of the Willmore energy, but let's say with a prescribed genus, since we already know if we don't care about the genus, the absolute minimum is just 4 pi. So we could go genus 1. And the genus 1 case was actually recently, in the last 10 years, resolved. This was a very, very difficult result that was open for about 40 years. This was basically a 100-page annals paper. What they showed is that for all tori, the Willmore energy is at least 2 pi squared, and it's actually attained, and it's attained exactly when your torus is a conformal image of basically this model torus, which I've written in R4. So this is a torus that's a product where I have the first 2 factors in R4 squaring to a half, and same with the second 2 factors in R4. So if we're interested in higher and higher genus, trying to go explicit in terms of finding the actual minimizers is probably not going to happen, because given the difficulty of this result in comparison to the first. And in fact, much, much, much less is known. So only the existence part of the question for minimizers of higher genus is known. There's very little known about actually what these higher genus minimizers actually look like. So this was more recent work. So Leon Simon in 93, and then Bauer-Kubert basically completed the proof. So if I define a number beta sub g, which is the infimum of the Willmore functional, when I consider all genus G for some fixed G embeddings, I would like there to be a surface which actually attains this infimum. And this is what they proved. So there exists a smooth embedded surface with genus G, which attains this infimum. So why is this result have a 10-year basically gap between the contributions? Because there are some difficult calculus of variations issues one has to confront. So the general idea of the proof of this is very, very simple. It's called the direct method of calculus of variations. And one does basically the simplest thing you can think of. I have an infimum, I have this beta G. And what I will simply do is take a sequence of surfaces whose energies approach the infimum. And I will do the only thing I can think of, which is to try to extract a convergent subsequence from these surfaces. Now, this is a very formidable task because I just have a sequence of surfaces and I need some kind of smooth convergence. I need to make sure that in the limit, I don't lose genus, that things still stay smooth, and so forth. And there's very many ways you can imagine divergence, actually a sequence not actually converging. So I will discuss 2 of these issues. And so what Simon did was in 93 was actually verify this just in the torus case. And he was not able to basically handle the general genus case. And this is what Bauer-Kubert did. So I want to discuss maybe 1 or 2 of the things that we could imagine going wrong in this compactness argument. So what can go wrong if I take a sequence of surfaces? How could they potentially diverge? So the first possibility is that we could have what I call divergence in moduli space. So suppose I'm looking for a minimizer of genus 5, say, so that's 5 handles. To the right, I have some cartoon pictures of minimizers of genus 3 and respectively 2. So I'm going to play some games with those for just a little bit. So I know always I can play these conformal transformation games. What I'm going to do is, for each of these surfaces, individually sort of blow them out. So these handles get smaller and smaller, and those surfaces become more and more like spheres. I can do that at no cost in the Willmore energy. So these latter pictures are still minimizers of genus 3 and 2, respectively. And now what I can do is, if I'm looking for a surface or a sequence of surfaces that are going to the infimum for genus 5, is I could imagine basically cutting off the handles, the genus 3 one, and then placing them on top of a cut sphere that had the genus 2 handles. And then coming up with a sequence that could go to the infimum where I have handles that keep getting smaller and smaller. So this is a possible problem, because if this could actually happen in the limit, I could have non-convergence, because I could basically having handles just sort of drifting off. And so what these examples show is that if I'm looking for the infimum of some G, this is less than or equal to the infimum of the beta G plus 1 and beta G plus 2 minus 4 pi for any G1 and G2 that sum to G. The minus 4 pi is because if I had 2 of these pictures, I have to cut off the cap for one of these, and I lose basically the 4 pi from the sort of limiting sphere, and then I glue on just the cap that's holding the genus to the second one. But I don't want this to happen. I want to show that this can't happen, so that my sequence actually converges or has a convergent subsequence. So to rule out this possibility, one actually needs to prove a strict inequality in this inequality above. So if one can prove the strict inequality, then you can basically never see this sequence of pictures that I just showed, if you're going to the infimum, which is where you're looking. So this is what was done by Bauer-Kuber, and this was the reason for the 10-year gap in between. So the calculus of variations methodology is very analytic, and this is basically what Leon Simon did. But this gap that was basically plugged was really a geometric fact that they proved. They had to find a nice geometric way to rule this out. And so this sort of interplay is what's sort of subtle about this kind of problem. So there's another possibility. So another possibility is that I could have a sequence, a minimizing sequence, where my surfaces sort of get closer and closer to 2 spheres, more or less like the picture I had above of this doubled sphere. So a sphere with a smaller sphere inside it, and then maybe handles that are sort of shrinking to 0. And the worry is that in the limit, I could get basically a sphere that's exactly covered twice, and the handles have popped, they have shrunk to 0. So I don't get a smooth surface with genus G, I get a sphere with multiplicity 2, which is not what I want. So Rob Kushner in the late 80s showed that for these Lawson surfaces that I had some pictures of before, that their Willmore energy was always strictly less than 8 pi. Remember, in those pictures, they look sort of like 2 spheres with these handles. So the Willmore energy of exactly 2 spheres is exactly 8 pi. What he showed is basically you lose some energy by adding those handles. So what does this mean? This means that you can never see in the limit a sphere with multiplicity 2, because the infimum is strictly less than 8 pi. So this possibility I described can't happen. So that's great. So this is a very, very simplified exposition of the story behind this the proof by Leon Simon and Bauer-Kuber. There are many, many more technical issues I'm not discussing here. But I want to switch gears now, and I want to talk about a constrained version of the preceding problem. So I still want to talk about bending energy, but I want to add an extra geometric constraint. So the idea for this problem comes from some biophysicists. So Peter Canham in the early 70s proposed a model that should explain the shape of a red blood cell. So if you've ever looked at a picture of a red blood cell, they have this kind of funny, what people call bioconcave or biconcave shape. So they're topologically spheres, but they're dented. They're dented at the top and bottom. And before the 70s, I think there was no real model to explain this shape. On the right, I have pictured here another vesicle that actually has genus 2. So if you look carefully here, there's a hole there and there's a hole there. So it's a closed surface that has genus 2. So what is the Canham problem? If you're thinking about this model of the shape of a blood cell or one of these vesicles, you care about the bending energy. So you want to minimize this Willmore integral, the total bending energy. You have some prescribed genus, but you really care about the area and enclosed volume. So you only have a certain amount of material, so you fix the area, and then you fix the enclosed volume, say, because your vesicle has to enclose some liquid, say. So now you have 2 constraints, area and volume. Then you want to play the same game. So first, I want to describe some simple mathematical reductions. So it's actually very easy to go from 2 constraints to 1. So we're mathematicians, so we care about the right way to think about a particular problem. This functional, Willmore functional, is scaling invariant. If I just dilate my surface, the total bending energy doesn't change. So that means I could normalize either the area or volume B1 if I'd like, and just consider the other. Or even better, I can fix the scale invariant isoperimetric ratio, say. So here, if I have a surface sigma, the V of sigma is my isoperimetric ratio. So I take the volume cubit area, volume squared area cubit, so I get quantities in the same units, and then divide. And this will be my 1 constraint now. So I picked this for particular normalization because when I do this, my isoperimetric ratio is always between 0 and 1. 1 exactly if I'm a sphere. So that's what the isoperimetric inequality says. So if I have isoperimetric ratio very, very close to 0, it means I enclose very little volume in comparison to the amount of area I have. Okay. So I have one slide here that is just attempting to introduce what I think is a really, really cool phenomenon. So let's think about sort of dimensional analysis just for a second here. So for the generic surface in R3, and I think about the conformal transformations, I want to think about which ones actually change the shape of my surface. So again, I have scaling invariance. So I don't care if I rotate my surface or actually scale it just bigger or smaller, that doesn't change the shape. So only the inversions really change the shape. And I have as many inversions as I have points basically in R3. So more or less, there's a 3-dimensional space of these inversions. What this means is that if I'm thinking about minimizers to this problem, I have the functional, I have 1 constraint, but I have 3 degrees of freedom in terms of making Mobius transformations, conformal transformations that don't change the energy, but may change the isoperimetric ratio. So this heuristic says that generally I should expect non-trivial families of minimizers. So if I have 1 minimizer, probably I have many more. I say probably because not a whole lot has been known until recently about actual minimizers for this constrained problem. However, empirically, some biophysicists observed this in the lab, actually. So they found these vesicles, they have pictures of them in real time, videos of them actually doing this. So these are some pictures of a genus 2 vesicle, time lapsed by about a couple seconds in each case. Its shape is actually changing. So it's sort of, they call it conformally diffusing. It's actually moving around in a way that its total bending energy is the same, and it's sort of randomly moving around. And here I have some computer pictures of roughly what this looks like if you have sort of abstract surface, some handles moving around. So this is just sort of a unusual phenomenon. I think it's very interesting. So now I want to turn to the question of actually rigorous existence for minimizers of this constraint problem. So this is basically everything that's been known has been known in the last 10 years. So it's a more challenging problem. So first in 2011, Shigula did this for the genus 0 case. He proved the existence of sphere minimizers for arbitrary isoperimetric ratios. And then there's a group of 3 mathematicians who did this for general genus, but isoperimetric ratio not very small. So I won't go into how not small it is. And then just this past year, for this year, Christian Schar, was a PhD student at the time, he did the general isoperimetric ratio case, but just genus 0 and just genus 1. He was able to do those 2 because in each of those situations, you can work in a rotationally symmetric situation. So you can come up with models and heuristics that are always rotationally symmetric. So he was able to push that actually pretty far. And then my collaborator, Rob Kussner, and I, in April, closed the door on the general problem. So we did general genus, general isoperimetric ratio. So finally, the existence part of the question is now well understood. So in the remaining time, let me see how much time I have. Oh, I have plenty of time, I think. So I want to talk about some of what we did and some of the pitfalls. So like before, like with the unconstrained problem, we want to use this direct method of calculus variations. So I want to take a minimizing sequence and try to extract a convergent subsequence. This time, my beta G, which before was just the infimum of the Willmore energy for some genus G, now has to have a V, has to have an isoperimetric ratio. So I actually have a function beta G of V. So for each fixed V, I take the infimum over all surfaces with genus G and that particular isoperimetric ratio. And then I would like, of course, to find a smooth surface with genus G and isoperimetric ratio V, whose Willmore integral is beta G of V. Okay, so that's clear. And now we have to confront the same obstacles we had before, except there's a little bit more. So we have to confront basically the same issues we did before, the possibility that I could have this divergence in moduli space, the possibility that I could have this convergence with multiplicity 2, but every time I have to only be looking at surfaces that have this fixed isoperimetric ratio. So I have to work a lot harder. In particular, if you're remembering that the Willmore function is conformally invariant, in the preceding case, you always had the freedom to take your surface, whatever surface you had, any surface in your sequence, and then apply to it any conformal transformations, because that would not change the Willmore energy. So if you had a minimizer and then you started conformally moving it, it would still be a minimizer. Not so in this case, because if I have a minimizer, I can only do conformal transformations that would preserve the isoperimetric ratio, if that's what I care about. So there's a whole new world of difficulty one has to work with. And this is basically why this problem was not solved in 2003. Okay, so Montino-Schar basically proved that you do not have this problem of the divergence in moduli space. So they did the analogy of what Barrett-Kubert did in 2003, but just this past year, a year ago. Their preprint came out in November and their preprint was accepted in March, I think. So they proved basically this other inequality that I wrote up with the pairs of handles drifting off. And so they reduced it to just proving that the beta sub G of V is strictly less than 8 pi, which is the second possible problem that I mentioned. And this is what my collaborator did. So we proved always for every G and then for every V, beta sub G of V is strictly less than 8 pi. So let me talk a little bit about how we did this. So the first reduction is that we really only need to prove this strict inequality for very, very small V, arbitrarily small V. So I only need to find surfaces that have really, really small isoperimetric ratios. So enclose a very, very small amount of volume and have area of order 1, say. The reason for this is these conformal blowing outs as before. So I can take any surface I have. So if I do have a surface that has very small isoperimetric ratio and energy strictly less than 8 pi, I can sort of blow it out conformally. This will not change the Willmore energy. I'll still be below 8 pi. But if I do this in a smooth way with these inversions, then I can make my surface look more and more like a sphere. So I can bump up the isoperimetric ratio because the isoperimetric ratio of a round sphere is exactly 1. So I can basically sweep all the way through the interval from very, very small, close to 0, to 1 in isoperimetric ratio just by doing these very, very cheap sort of conformal transformations that just blow out my surface. Okay, so now we turn our attention to thinking about very, very small isoperimetric ratio. So the heuristic or a heuristic for doing this is very simple. You want to find some way, somehow, a surface that has whatever genus you want and very, very small isoperimetric ratio and total bending energy about 8 pi, but crucially less. The heuristic is you want to construct a surface that looks like this doubled sphere I drew from before, because such a surface will have total energy about 8 pi, because it will be about the energy of 2 spheres, each of which is exactly 4 pi. Again, their size doesn't matter, but they'll be very close to each other, and then they'll have these little handles, which will have very small energy. So the idea is you want to take basically these 2 copies of a sphere, which here I've drawn as 2 lines, cut out G+1 pairs of disks, and then for each pair of disks, glue in a topological annulus, so that at the end of the day, after you do this G+1 times, you have now a surface of genus G. So what annulus should we pick? So there's a good model for the type of annulus we pick. This annulus is part of a catenoid. The catenoid is a surface of revolution in R3, and it has mean curvature exactly 0 everywhere. So why do I want this to be the model for my bridge? It's because the H is 0. So if I really care about the total bending energy, I care about the integral of H squared. So if I'm gluing in something that has H exactly 0, this is as cheap as I can get. And then the next thing I have to do is think about how I glue this to the rest of the surface. So this is a simple idea. Unfortunately, it doesn't work. So if you actually get down to the matter of what you need to do, you'll find that each bridge, after you smoothly glue it, always adds more bending energy than the little 2 disks that you cut out. So if I'm trying to get below 8 pi, I'm starting from 2 spheres. That's exactly 8 pi. I cut out 2 disks. I lose some energy. And the thing I glue in, I want to have less energy than the stuff I cut out. So if you just do this, you can't succeed. However, we did not give up because we were sure that this result was true. And so we decided to go to a higher order method. So we want the same type of surfaces that look more or less like 2 spheres with these little handles, but instead of starting with actually 2 concentric spheres, we have a higher order model for the regions away from these little handles that we have. So instead of using spheres themselves, we actually use graphs over the spheres of solutions of what's called the linearized Willmore equation. So if I take the sphere, which is a critical point for the Willmore functional, and perturb it, I can ask for all of the ways to perturb it as cheaply as possible. That will change the Willmore functional as small as possible. At the linear level, this is described by a solution on the sphere of this equation. So Laplacian on the sphere composed with Laplacian plus 2. So it's a 4th order operator. And so we're going to replace basically the 2 concentric copies of the sphere with graphs over sort of the sphere in the middle of solutions of this equation. And then we want to do this in such a way that those graphs sort of meet the catenoids that we want to glue in well. This is extremely vague what I'm saying because there are several variables. One, I have to choose where will I put these bridges? And so this is a difficult question that one has to answer. What is their sizes? That's another question. And then how exactly does one glue? And then how do those things, the information about the bridges themselves, interact with this equation here? So let me say a little bit more. So I want to talk about the locations of the bridges. So here's a picture of a decorated two-sphere. And so what we chose is to put the centers of the bridges at m points equidistributed about the equator of the two spheres. So here, these m points, I think m is 12 here maybe, are at the intersections of this equator line and then these meridian lines. So here, 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 etc. So this is a simple way that to have a fairly symmetric position bridges that are sort of equally spaced in some sense. This is what we picked. And now I want to consider what kind of function I'll use to be a solution of this equation. And so I can think of this operator in two parts, basically a composition of two second-order operators, the Laplacian and then the Laplacian plus 2 on the sphere. So I consider those operators one at a time. And I will be able to find a function that's in the kernel of just the Laplacian plus 2 operator that has actual logarithmic singularities at the points where I will put in the bridges. So it's a kind of a Green's function for this operator. It has singularities there, and then it's maximally symmetric. So it's symmetric under the same group, which is generated by the reflections through all of these meridian lines and then this equator line. So the function that I write down here has the same symmetries of that decorated sphere picture over there. And then what we do is the actual u that we take is some constant plus another constant times this b. So this constant is going to be related to this number tau, and this number tau is basically going to be dictating the size of the catenoidal bridges that I put. So each of these catenoids, it has a size, and that size I say to be, say, the radius of the smallest waist circle on the catenoid. So let's go back to that picture again. So this is rotationally symmetric, and there's the smallest circle there that I call the waist, and the radius of that circle I will call tau. So if I want to glue in m catenoids of size tau, I will also add to this function constant, and this constant is picked appropriately in a way that I'm not attempting to explain right here. So I know this is a lot of information, but in the simplest model, the naive model that I mentioned before, where we just do this, we just have the two parallel copies, you can think of this as a really, really naive model of the more general situation we use, where the graph function u is just a constant. So if I have the sphere and then I just take two concentric spheres, I can think of that as the graph of a constant function over the center sphere. That will give me on top a slightly larger sphere and on bottom a slightly smaller sphere. What we are saying is that's not good enough. I have to also have the additional freedom of not just choosing this constant, but choosing the amount of this singular function that I have. So this is what we do. And then by gluing bigraphs, graphs on the top of the base sphere and the bottom of the base sphere of this function u, cutting those off near the place where I want to glue in one of these small bridges, then close to the L, I put in one of those bridges and then smoothly transit from the bridges to the graphs of these functions. I can then construct smooth surfaces that have genus M or genus G, where M is G plus 1, and then have these very, very small catenoidal bridges. And then by making the tau very small, I can have surfaces that come closer and closer to two spheres. So the real question is, does this work? So do I get energy strictly less than 8 pi? Of course, since I'm standing here, the answer is yes. So we work hard, we do all of the estimates, and we show more or less explicitly that we can get 8 pi minus something positive. And the something positive depends on the genus, and then the size of these bridges we add. The bridges are going to be very, very small. So tau is small positive number here. And so we subtract something positive. So tau squared log tau, as tau goes to 0, is also going to 0. So the smaller the bridges are, the less that we lose, but we still get always below 8 pi. And when we do this, the isoperimetric ratio is going to 0 because I have less and less volume flows. So this is the end of the story for the existence part. I'm basically going to stop here. I would like to mention, however, so that's my last slide. I would, before I stop, I would like to mention that I said nothing about uniqueness or classification. So you'll notice in this whole talk, all I was talking about is existence. And the method by which these surfaces, these minimizers are constructed is extremely inexplicit. It's a compactness argument. So at the moment, basically no one knows anything about actually what these surfaces look like. Of course, numerically, there's been a huge amount of work done since the early 90s, but there's a lot of very, very interesting open questions about this. So I'd be happy to talk to anyone about any of these questions later. So let me stop there.
I don't know enough to ask a decent question, but you mentioned these biographs. Do they have geometrical interpretation?
They do. So they're solutions of this linearized Willmore equation. And you can think about that geometrically in terms of how you deform the sphere. So in some ways, so some solutions of those equations, for example, say the constant, or any constant is a solution to this equation. The constants correspond to just taking the sphere and dilating it to other spheres. So those are in the kernel of this operator, which means to first order, perturbing the sphere by one of those functions doesn't change the Willmore integral. And actually, for the actual constants, those correspond to just dilating the sphere, and that to any order doesn't change the Willmore functional. So there are the interesting solutions in the kernel of this operator do have geometric significance, but that significance is more complicated than just dilating the sphere. So for example, you take the sphere and you do any other Mobius transformation to it, it turns out since it's the sphere, you will just still get sphere. So it's not very interesting. But in particular, the singular solutions, the ones that we use that have logarithmic singularities, those transform the sphere in a different way. And I don't know a really good geometric way to think about those because they're not smooth, because they're singular. So they don't correspond to deforming the sphere in some manifestly geometric way, because if you do something very geometric, you're not going to lose the smoothness of the sphere.
So it's analytic rather than geometric.
Yes, when you're looking at the singular solutions, yes. So for when you're not looking at the sphere and you consider the analogous operator here, some of the functions that are in the kernel actually do have a more interesting geometric interpretation because you can relate them to the Mobius transformation. So at a nonlinear level, the Mobius transformations are not changing the Willmore energy, but you can see this at a linear level in the sense that if you take a function that corresponds to deforming in a conformal direction, it will be a solution of this analogous operator. And then you can basically see the conformal invariance at the linear level.
You need to deform those spheres in the same way you have two spheres initially, you apply the same U to inner and outer.
Yeah, so that's actually a very good question. So I'm cheating in a little bit of what I said here for something that's very much related to that. So in R3, if I think of the base sphere as, say, the unit sphere, the inside and outside directions of the sphere are obviously very different. What we actually do is we, using the conformal invariance, port everything over to S3 first. And then the unit sphere in R3 becomes the equator sphere in S3. And there we actually gain a little bit because in S3, the two sides, the inner and outer, are actually the same. They're isometric. So in S3, we do the same thing basically on the top and the bottom because it's convenient and we can. And then we stereographically project everything into R3. So that operation doesn't change the Willmore energy. So if we get below 8 pi, we're happy. It will change a little bit the isoperimetric ratio because once I go into R3, things are not preserved, but they're very, very close. And if my only interest is getting very small or arbitrarily small isoperimetric ratio, I don't care how it changes a little bit when I do the stereographic projection. So the answer is basically, we do the same on the top and the bottom, even though in R3, it won't be the same because they simply look different geometrically.
Any more questions?
So Peter, thank you very much for the talk. So this equation that we see now on the slides and the one you started with, so can you explain a bit about like how they are related? And then the second question is, well, now you and Rob entitled to the prize that Napoleon gave.
All right, I say the last question again, the prize that.
So are you now entitled to that prize that Napoleon promised?
Oh, no, Sophie Germain won that prize in 1816. So I think the answer is no. Right, so from the very, very beginning, let's see if everyone's okay with back to the beginning. So there was this equation here drawn up at the beginning. You'll notice there's a difference here. There's a time parameter here. So if what you do in this latter equation, if you basically separate variables and look for solutions that only depend on the position multiplied by the time, the standard technique in PDEs, the equation that you'll get for the spatial part is just the Laplacian of the Laplacian of u equals 0. So there will be no time left, and you just get this biharmonic equation. So that's, again, still a fourth order equation. And then this is what's exactly analogous to that equation we wrote down for the sphere. So the linearized Willmore equation for the plane is the Laplacian of the Laplacian of u. Plane is not a compact surface. So if you're considering non-compact things, if you really want to study them carefully in the regime I was working on after the first slide, you have to be a little bit careful, but that's basically the story.
Any questions for people generally?
Have you made any physical models of the surfaces that you'd shown us pictures of before?
So I have not, lots of other folks have. So there's many, many papers about different numerical methods for these kinds of things. So I put up a couple pictures at some slides, but there's a whole zoo of things that people have looked at. So you can see very, very interesting things. Yeah, it's sort of the funny thing is that the sort of rigorous existence part has really lagged behind basically everyone else in the field, in the sense that in the early 90s, the biophysicists were writing these really, really exciting papers about what's going on and the predictions and various things. But since it's basically a fourth order problem, it's been tough for us to sort of catch up with that.
It has to be false
So that's a good question. So short answer is no, but there's an interesting sort of functional analysis point that maybe now I'll address just a little bit. So if you want to do a thought experiment, here is the Willmore equation. As I mentioned before, this equation is a little bit difficult because this is a nonlinear equation sort of hidden here because this Laplacian actually depends on the immersion. It depends on the embedding. So it's not, even this dominant part is not linear. The problem is if you think about sort of variationally what's going on, so the functional that I'm considering is the integral of the square of the mean curvature. So the functional analysis point of view is basically to take that as your beginning and say, let's consider immersions that, and this functional, and I want to consider basically the weakest possible immersions I can for which this functional makes sense, this energy makes sense. So if you do that, you need the mean curvature function to be L2 because you need its square to be integrable. On the other hand, if you do some naive Euler-Lagrange calculus, the variational equation is this equation. This equation, inside the equation, you see the mean curvature cubed. And that means that the mean curvature needs to be L3, which is a stronger condition than the mean curvature is L2. This is what Tristan Riviere calls the functional analysis paradox here, is that equation that you get from Euler-Lagrange equation has a stricter, more stringent requirement than what you expect you get from the energy itself. And so this is one of the reasons why the analysis side of things has been very difficult. So about 15 years ago, 2006, Tristan Riviere, so this equation here has been known for 100 years. In 2006, Tristan Riviere basically found a way to not reduce the order, but he did a little bit of uncoupling in the sense that he discovered that if you pick good coordinates on your surface, you can rewrite this equation into a divergence form equation that basically gets around this functional analysis paradox. And then you get a system because you get a second equation that governs the coordinate system that you need to choose. So in some sense, the answer to your question is yes, you can play some tricks that make your equation better, but you can't reduce the order of the equation.
Yes, let's thank Peter again and for the talk. Maybe all last questions. You can direct directly to Peter.
Okay, thanks so much, everyone, and everyone on Zoom as well. Let's see.
Okay, Peter, I see you in a little while, yeah?
Yeah.